Good morning, everyone. Happy Friday. So today is November 3rd. So we have homework 7 and quiz 4 due. Okay? So make sure you finish your quiz before midnight tonight. You know, homework, even though it's past the due date, you can still open a new attempt to increase your score. Right, everybody? But the quiz, you gotta finish before midnight. Otherwise, it'll be closed and you cannot get in anymore. Okay, and then this weekend you can work on the practice exam, right? So exam 3 is next Wednesday. The practice exam is on the website, right, everybody? If you have questions, ask me. So you can either come to my office hours next week or email me. If you cannot come to my office hours, you can email me and then we can find time to meet. Maybe if it's in the evening, we can go to TED Live and meet. Okay, everybody? And let's see. Okay, so today, hopefully we will finish 6.2 and also finish 6.3. We are one lecture behind because of the projector. Okay, let's see. So last time we were talking about applications, optimization, right? Do you still remember the steps? You want to see what a node to be optimized. Usually you look at the last sentence, right, of the problem. It tell you, okay, maximize the area or minimize the cost, something like that, right? Okay, and then step 2, draw the picture. What is involved? What's the shape? Is it a cylinder, or is it a triangle, or is it a rectangle? Okay, so draw the picture. And also set the variables. So when you set the variables, ask yourself, what is constant? What is changing? So for the quantity that is changing, then you can set the variable, right? But for some quantity remain the same all the time, then do you need to set the variable? No, just put the number there. Okay, everybody? Because it's not changing. And then, yes, you can name X for horizontal distance, Y for vertical distance, A for area, V for volume, R for radius, H for height. And step 3, you want to list relations and you want to express the unknown quantity that you want to optimize. Express this as a function of a single variable. Sometimes it might be a function of 2 variables, then there must be other relation. You can express one variable in terms of the other, then you can substitute back. So you only have a function with one variable, right, everybody? Okay, then we want to find the maximum or minimum. So we want to take the derivative, find the critical points, and find the domain. Draw the picture, right? And then the domain separated by the critical points, and then depends on your derivative and the function, increasing, decreasing. This is max, right? Decreasing and then increase. This is mean. Okay, everybody? Right. And then finally, you see whether the value are possible. Okay, you cannot have negative area. Okay. So last time we did example 1, example 2, and we were in the process of doing example 3. Do you still remember? I would say we have the window here. We want to let in the most light, which means you want to maximize the area. Right, everybody? Yeah, bigger area, we can let in more light. So here, area is rectangle and half circle. So we get, this is the area. You see, we want to maximize the area, so we want to take the derivative. But this is a function of 2 variables, right? We cannot differentiate a function with 2 variables. There must be another relation we can reduce the number of variables, right? And the other relation is here, 12 meter. You can look at the units and then you can figure out what it is. Meter is length, okay? Perimeter is length, right? And meter square is what? Area, right? Square, meter square, area. And meter cube is volume. Cube. Think about cube. Length times width times height. That's why it's meter times meter times meter, meter cube. Right, everybody? That is volume. So look at the units, then you can see what quantity it represents. Length, area, or volume. And then so for the perimeter, we got it's 12. And well, sometimes there are more than one ways to solve a problem. And then you want to find a way that is easier. In this case, solving H in terms of R is easier. Yes, everybody? So this is what we did. And then we plug in the area. So we get also simplify before you take the derivative. By the way, you don't have to take the derivative here, right? It's pattern through and then this. It's so complicated. So you expand it, then you only need to use the power rule, right, everybody? And therefore, this is the derivative. And we set this equal to 0. We want to solve for r. So we move those two terms to the other side, and we factor the r. Therefore, r is 12 over pi plus 4. Is that okay, everybody? Let's continue. Okay. Let's continue. Oh, I don't have enough space. Let me change this a little bit. So this is a good part about Word. I can circle this and I can shrink it. So then I have more space. Okay, let's see. Okay, so we find the derivative, set this equal to 0, and next we want to find the domain. What's the domain of R? What is the largest R possible? What is the smallest R? Well, the smallest R, your R could be smaller, smaller, smaller until you get 0, right? If you get 0, look at your window. If your R is 0, you actually only have those two sides. Do you agree, everybody? You kind of break the 12 meter into half, so 6 meter for this side and this side, and your R is 0. In this case, your area is what? 0, right? Your area, you only have two sides, okay, together, so your area is 0. What is the biggest R? Well, the biggest R is, so your R is bigger, 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 then you get your window like this. Just a half circle. Your H is 0. Do you agree, everybody? This is the biggest R possible. Okay, your H is 0. Then you know the framing materials is 12 meter. So it means the perimeter of this figure is 12 meter, right? And what's the perimeter? We have a half circle, half circle is pi r, right, everybody? And actually, in general, if you have angle theta, and this is r, then the arc length, you can write this down. The arc length equals theta times r. This is the arc length, okay, which is this side. And the area is 1/2 theta r squared. So did you learn this in track? Yes, okay. That's why here my angle is pi. So the length is pi r. So this is pi r. This is r. This is r. So we get pi r plus 2r. That's all the framing materials. That's 12. Oops, pi r plus 2r. Therefore, you can factor out r on the left. Pi plus 2 is 12. And r is 12 over pi plus 2. This is the maximum r. Okay, so your domain is from 0 to 12 over pi plus 2. Is that okay, everybody? That's the smallest r is 0. Then our h is like 6. Biggest r, your r is bigger, then your h is 0. Okay, so the framing materials together is 12, so we find r is 12 over pi plus 2. Okay, now draw the picture. So it could be 0, it could be 12 over pi plus 2, and you see 12 over pi plus 4 is between them? Yes, because see here, bigger denominator, it means the fraction is smaller. Yeah, everybody? Bigger denominator, it means the fraction is smaller. So, let's see. Area prime and area. That is the critical point. So the A prime is 0 here. Alright, let's pick a number here. Well, we can pick 0, right? Everybody? Pick 0, we plug in positive or negative. If r is 0, what do you get? Positive. Yes, positive. And then think about this. If r is so big, if r is so big, when you multiply by these, it'll be bigger than 12. And your answer will be positive or negative? Negative, if r is so big. Right? You subtract a bigger thing. So this would be negative. Questions? Circle here. Oh, we were looking for the domain of r. So what is the smallest r possible? The smallest r is 0r is, okay, this is your picture. If you have a smaller r, then your h will be longer, right? And then even smaller r, your h will be even longer. Do you agree? So the smallest r is when your r is 0. You actually only have 2 spaces of the window. So the area is 0. Right, everybody? How about the largest r? Well, if your r is bigger, your h is smaller, right? The largest r is when the h is 0. When h is 0, the perimeter is pi r and there's 2 pi's. 2r, you add them together is 12. So r is 12 over pi plus 2. Is that okay, everybody?
So you plug the 0 into the first one.
We put the 0 into the A prime, not the first formula. The derivative. Do you remember how do we find maximum minimum?
Yeah.
We find the derivative, find the critical point, find the domain separate the critical point. Then you plug those, pick a number on the interval, plug in the derivative. Yeah? And you see positive. Here you pick a number. If you don't know what this number is, it's okay. Just imagine if r is so big, where 12 minus a very big number, then it will be negative. Yeah, everybody? But if you have your calculator, feel free to put this in your calculator and then put this here. You also get negative. Yeah. If your A prime is positive, then your A is increasing or decreasing? Increasing. If your A prime is negative, then your A is decreasing. So what is that? Maximum. See? We get maximum area. Is that our goal? To get maximum? Yes. So it always match with our goal. Okay? Otherwise something wrong, go back and check your work. So get maximum area when the R is 12 over pi plus 4. Because we want to know all the dimension. So we also want to know h. But what is h? 6 minus... Okay. Do you see here I can factor out the r? We get pi over 2 plus 1 times r. Here. See, I can factor out the r, then I get minus pi over 2 plus 1. Yes. And then the r, put the r to be this number. So we get 6 minus pi over 2 plus 1 times 12 over pi plus 4. And then you can put this in your calculator. You can put this in your calculator. Hopefully you get some decimals. You can get 3 decimals. So far, so good, everybody? Yes. So this is the example 3. Any questions about example 3? No? All good? All right. So let's continue. Okay. Wow. 17 minutes. Okay. My goal is to finish this session in 6.3. Okay, let's see. Oh, so I just turned off my phone. Okay, thank you. Alright. A man launched his boat from point A on a bank of straight river, 3 kilometers wide, and wanted to reach point B, 8 kilometers downstream on the opposite bank, as quickly as possible. He can row 6 kilometers per hour and run 8 kilometers per hour, which makes sense. You run faster than you row, right? Where should be landed? So to reach point B as soon as possible. So we're looking for the D, okay? So where should be landed? Like the D is between C and D, right? If D is C, then we just go to point C and then run, okay? Or a B is just completely row on the river, right? You ready? So we want to know where is D. Okay, let's set the variable. So let x be the distance C and D. So let x be the distance CD. Okay, and our goal, fastest, as soon as possible. So our goal is to minimize the time. Usually time is the independent variable, but here time is actually the dependent variable. Okay, we want to minimize the time. Alright, so time is the time on the river plus the time on the land. Do you agree, everybody? And time is distance over speed. Yes, everybody? Time is distance over speed. Okay, time on the river. Well, time on the river, well, the distance on the river. Do you see the distance on the river is AD? Yeah. And the speed on the river, what is the speed on the river? 6 kilometers per hour. And then distance on the land is what? dB. Yes, everybody? What's the speed on the land? 8. Okay, now we want to find AD. Do you see this is the right angle triangle? And with this side is 3, this is x. What is the hypotenuse? Pythagorean theorem, what is that? Square root of, what's Pythagorean theorem?
A squared plus B squared equals C squared.
Yeah, so this side, AD, is square root of 3 squared plus x squared. What's 3 squared? 9. Okay, 9 plus x squared over 6. dB. Ooh, do you see here the total is 8, and then this is x? What's dB? Yeah, 8 minus x over 8. Is that okay, everybody? All right. So we want to differentiate it. Okay, make this to the standard term. Okay, standard term. This is 1 over 6 times 9 plus x squared to the 1/2. Do you agree? Square root is 1/2. And then let's split this. 8 over 8 is 1, bless you, minus 1 over 8 times x. Yes, everybody? We split them so that it's easier to take the derivative, right? Let's take the derivative. Okay, t prime. Do you see here we use chain rule? So 1 over 6, u to the 1/2 derivative is 1, oh yes, 1 over 12. So 1/6 times 1/2 times u to the negative 1/2 times, very good, u prime, which is 2x. Okay, and then derivative of 1 is 0. Derivative of minus 1 over 8x is, yeah, 1 over 8. Oh, do you see this 2 and this 2 cancel? Because that 2 is on the numerator, that 2 is in the denominator, right? So this is x, yes, over 6. And then this square root is actually in the denominator. Right, everybody? Okay. Yeah, this function is harder. Yes, this example is harder than the example we did before. So we want to find the critical point. Okay, set this equal to 0. Right, everybody? Okay, so yeah, one way is to take the common denominator and then combine them, okay? But in this case, this is complicated. So you can solve for x by move the 1 over 8 to the other side and then cross multiply. So move the 1 over 8 to the other side. Maybe let me use a different color. Okay, so we're in the process to solve for x. So x over 6 square root of 9 plus x squared equals 1 over 8. So we add 1 over 8 on both sides. Is that okay, everybody? And do you remember if both sides you have single fraction, then you can cross multiply. This is only if you have a single fraction on both sides. The idea is really like you multiply by the common denominator on both sides. Okay, everybody? So what do you get? Ax equals 6 square root of 9 plus x squared. Yes, everybody? Do you see 8 and 6? We have common factor 2? divided by 2, what do you get? Get 4x equals 3 square root of 9 plus x squared. Yes. Get rid of the square root. So both sides square. Okay? So square both sides. Okay, Blaine, what is 4x squared? Square. 4 square. 4 square, 4 times 4?
Oh.
Yes. So 16 and then x squared, right? Okay, Will, what's 3 square? 9. Oh, then you see the square root and square cancel. Look at 16x squared. 9 times 9 is 81 plus 9x squared. Oh, you see? Move the 9x squared to the left. Page, what is 16x squared minus 9x squared? 7x squared is 81. So both sides divided by 7. And we take square root. Remember when you take square root, you get plus or minus, always. So you get 81 over 7. Oh, 81 is, square root of 81 is 9, right? And you have 9 over square root of 7. And your x, think about the domain, your x. Okay, can your x be negative? Can you go backwards and go here? You can, but we know it won't be the shortest time. Do you agree, everybody? So if you want to find the shortest time, D should be between C and X should be between B is between C and B. So X, the smallest X is what? So domain, the smallest X is 0. And the largest X is down J. What's the largest X? Oh, okay. Mackenzie, what is the largest X? So D is here between C and B. The smallest X is when you have 0. The largest X is 8. Yes. So the domain is 0 to 8. And so we draw the table 0, 8. Do you see? Now we only take the positive root. We don't pick the negative. Okay, 9 over square root of 7. And you have t prime and t. Okay, let's think. This integral, well, we can take 0, right, everybody? So this is the root. So you know t prime is 0 as the root. And this part, we can take 0. Right? Yanni, if you plug in 0, what happens? This is 0, so we get a negative. Okay. And then, if you plug in 8, hopefully this thing will be bigger than 1 over 8. So you get positive. So increasing or decreasing? Decrease and then increase. Oh, you see that is the minimum. Are we looking for minimum? Yeah. So we get minimum time when x is 9 over square root of 7. And you can also put this in your calculator, and then you can round your answer to 3 decimal places. Yeah, I'm okay with that. Yeah, this is exact, so I'm okay with that. Okay. So far, so good, everybody? Yes. This example is harder because the derivative is more complicated. Yeah. Okay, next one. Okay, so example 5. A rectangular garden is built with one side against a barn. 200 meters of fencing are used for other 3 sides of the garden. What dimension maximizes the area of the garden? Okay, so you have a barn. This is the barn. And you have a rectangular garden. So something like this. 200 meters of fencing. So this is 200. And are used for the other 3 sides of the garden. So let's set the variable. Do you see this is like the vertical distance? So we use y. And this is the horizontal distance. We use x. Is that okay, everybody? And we know the length of the 3 sides. What's the length of the 3 sides? Y plus x plus y. Together is 2y plus x. Exactly. And we know the length is 200, right? You have 200 meters fencing materials. Okay. And then you want to maximize the area. What's area of a rectangle? Yeah, length times width. So x times y. Yes, everybody? So we want to maximize the A. So far, so good? Everybody? Okay. Sometimes, like the problem could be more complicated. Like, if I say, okay, let's spend some money. Like this side and this side, let's spend like $5 per meter or per feet. Okay, on this side. And on this side, the fencing materials is $2 per meter. Okay, then you want to minimize the cost. Okay, so let's say you have $1,000 you want to spend. You want to minimize the cost. And you want to make sure your area equals a number. So you have a lot of different variations of this pattern. Okay, everybody? So read the problem and set up the relations. Okay, now let's see. We want to maximize A. Well, do you see A is a function of 2 variables? We want to reduce that. For x and y, we have some relation. Question. Do you want to solve for x in terms of y, or do you want to solve for y in terms of x? Yes. X in terms of y. Then you get all the numbers are integers. If you solve for y in terms of x, you need to divide it by 2, so you have fractions. So even though you can do it both ways, but we like to avoid fractions, that's easier. So, okay, here x equals 200 minus 2y. Yes, we solve for x. So we subtract 2y on both sides. Okay, now my a is x. Replace x by 200 minus 2y, and then times y. Is that okay, everybody? All right. Do you like product rule or power rule? If you take the derivative here, you need to do product rule. If you distribute, then you only need to do power rule. Which one is easier for you? Huh? Power rule, yes. So we distribute. We get 200y minus what? 2y squared. Oh, yes. Okay, down J, what is the derivative? So 200 minus 4y. Yeah, see? We set this equal to 0. What is y? Joseph, how do you solve for y? Huh? Yes, subtract 200 and divided by negative 4. Oops. So what is y? What? 50, yes. Okay, good. So now, what do we do? To the domain, right? We need the domain to draw the table, right? So what is the domain? What is the smallest y possible? Leila, what's the smallest y? 0, yeah. If the smallest y is 0, it's like, ooh, I only have the x. Do you agree, everybody? How about the largest y? Or the largest y is 100. Your x is 0. You all use all the materials to build a y. Can you imagine, everybody? So, because the total is 200, and each of them is 200 over 2 is 100. Yes, everybody? Oh, okay. 15 is in the middle. So 0 to 100. 15 is in the middle. Alright. A prime. What's A prime? Well, at 50, A prime is 0 because that is the critical point. This interval, what number do you plug in? 0. You plug in where? Do you plug in A or A prime? A prime. Ooh, so what do you get? 100. Yes. And page here, what number do you plug in? We do 100. Ooh, we plug 100. What do we get? Positive or negative? So 200 minus 4 times 100 is negative. Okay. Dante. So your A increasing or decreasing? Increase and then? Yeah, maximum. Are we looking for maximum? Yeah. So get maximum area when the y is 50. What is x? Yeah, 200 minus 2 times 50 is 100. So far, so good, everybody? Yes. So this is example 5. Okay. Because today we're behind schedule. Could you do example 6 at home? I have the solution on the website. Could you do that? So try example at home 6 at home and then look at the solution on the website. If you have questions, come to see me. Okay, so 6.3. Yes. So today we should start 6.4, but yeah, but at least I want to talk about 6.3. So further business applications. Okay, elasticity of demand. Okay, so elasticity, it measures the sensitivity of demand, how a change in price affect the demand. Okay, so if your price increase, your demand go down, right? Because it's more expensive, you don't want to buy it. If your price is cheaper, your demands go up, okay? Yeah, but sometimes some products is very sensitive. So small percentage changes in price can have a significant effect on the demand. For example, cars, home loans, jewelry, and concert tickets, right? A small percentage of changes, but it really affects on the demand, right? Okay, but some products are not quite sensitive, like milk, heating fuel, and light bulbs, because you need milk all the time, right? Home and jewelry, you you don't need to buy it now, you won't die. But milk or like pasta or bread, vegetables, you need this every day, right, everybody? And also light bulb. If your light bulb is broken, you need to buy another one. You cannot live within that, right? So in this product, it's not quite sensitive. So elasticity, oh, how do you pronounce it? Elasticity, yeah, of demand. Okay, so let Q be f of P, where Q is the demand at a price P. So the demand depends on P. Okay, the demand is a function of P. Then the elasticity of demand is the following. So negative P over Q times the derivative of Q with respect to P. So Q is a function of P. Here you take the derivative. And then you multiply by negative. So how I remember it, it's like negative reciprocal. Okay, but we don't take the derivative. This is the derivative. Here is the P and Q, the derivative. So you have dq over dp, and then here is the reciprocal, so P over Q. Okay, everybody? So this is the formula. Okay, demand is inelastic, so not quite sensitive if the E is less than 1. Is that okay, everybody? Demand is elastic, sensitive, if E is greater than 1. And then demand has unit elasticity if E equals 1. So this is terminology. Okay, everybody? Alright, let's look at example 1. Terence Wells described the demand of distilled spirit as Q equals F of P. So this is the function. Demand is the function of price, where P represents the retail price of a case of liquid in dollars per case, and Q represents the average number of cases purchased per year by a consumer. Calculate and interpret the elasticity of demand when P equals $118.3. Okay, so this is Q. We find the derivative. What's d q d p? What's the derivative of this function? Joseph. What's the derivative of this function? Yeah, just the negative 0.00375. Right, everybody? And next term derivative of constant is 0. Okay, so now our Y, we plug in. negative P. So P is P, right? But Q, look at this. Q is negative 0.00375 P plus 7.87. Is that okay, everybody? This is P over Q times the derivative. Oh, the derivative is this negative 0.00375. We plug this here. Is that okay, everybody? Do you see this negative and this negative cancel? Yeah, these two negatives cancel. Questions. Can we cancel this number and this coefficient of B? Can we cancel those two numbers? No, because this term does not have this as a common factor, so we cannot cancel. So we get 0.00375 P over negative 0.00375 P plus 7.87. Is that okay, everybody? You will just plug in the formula. Now I want to find the E when P. So we plug in P is 118.3. So then our E is, see, plug in. The E is 0.00375 times P. What is P? 118.3. Denominator negative 0.00375 times P 118.3 plus 7.87. What do you get? Everybody take out your calculator, put this in your calculator. What do you get? Hopefully you get a positive number. Yes.
0.0597.
Thank you. Very good. So we want to compare this number with 1. Is it bigger than 1 or less than 1? Oh, it's much less than 1. So what do you say if E less than 1? Yes. Very good. So demand is inelastic. Okay, so it's not quite sensitive. Okay, everybody? It's not so sensitive to the price change. Okay, and also, what does this elastic means? It also means that if you have an increase in the price, then you have the decrease of the demand. You know, price goes up and then demand will go down. Okay, so this numbers, it means that, okay, so this means, so for example, if you have a 10% increase in price, then this will cause, you use this 10% and times the E, okay? The E here is 0.0597, well, which is like about 0.597% decrease in demand. Okay. So increase in price will get decrease in demand. But what is the ratio? For the ratio, with 10% of increase in price, you get the ratio times E, which is about 0.6% decrease in demand. So not so big compared to 10%. Is that okay, everybody? So the elasticity function is talk about like a ratio. So, and you have increase in price, okay, how much percent decrease in the demand. Okay, so let's continue on next Monday. Okay, have a nice weekend, and remember to do your quiz before midnight. And then the homework, if you didn't get like the full score 25 points, you can redo your homework until you get other points. And please also do your practice exam 3. Exam is on next Wednesday. Have a nice weekend.